Over seasonality again, and I'll go into more depth, especially in the last few slides. Okay, so we've seen examples in time series data. Often they're given in yearly, they're given in quarterly or monthly. They're given in some seasonal arrangement, which is repeated every year. So, for example, quarter 1, 2, 3, and 4, then again, then again, then again. So it's normally monthly or quarterly, but again, it could be any way that we split up each time period. And again, it's repeated year after year. Okay, so there's many examples of this, with retail sales. And again, it may be that there's some seasonal pattern to the time series data. For example, we often have that retail sales increase prior to Christmas, and this happens every single year. So we often find that retail sales are significantly higher in the quarter 4 than in quarter 1, say, and this repeats every single year. Similarly, we can have industrial production tends to drop in the summer, and there are many examples. So again, when there's some seasonal pattern to the data, especially when we're looking at the effect of one variable on another, we need to somehow model this seasonality. This is what we talked about in the first part of the lecture. So to give an example, this is the volume of retail sales in log. We see that every year there is a pattern. In the fourth quarter, every year sales are highest. Then they drop in quarter 1. Okay? We can then look at the growth rate. We can then difference this and look at the growth rate in sales. And again, we expect quarter 4 growth to be huge. It goes up, then it drops off massively in quarter 1. And this happens every single year. So we get this repeated seasonal pattern. So we need to somehow model this seasonality. There's two reasons. If we want to pick the model that best fits, to model the dynamics, the correlations, we need to model this seasonality. And especially important is when we want to look at the effect of one variable on another. So we may want to look at, say, house sales on retail sales, or the effect of one kind of retail sale on another, say, and so on. So if we're comparing variables, if we're regressing variables on each other that have seasonal patterns, we may start to find relationships between variables when there are none. We may find a spurious relationship. So just to check in once, is the feed working okay? Everything in sync? Just let me know if not, and I'll keep going. Okay. So the biggest problem then with seasonality, if we're looking often when we have time series variables, and you'll see this more when you start with Alistair on Friday, we're interested in looking at the effect of one set of variables on another. So again, if we have strong seasonal patterns in our variables, we may find correlations or relationships between variables which are not actually there. They're just coming just because they both move in a similar way all the time. And to give examples, for example, you take two very small countries with no real links to each other, and you compare the sales in one country with another, then because this seasonal pattern, if they have strong seasonal patterns, we're going to find a correlation between the two, even if there's no direct economic relationship between both variables. Okay, so this is why it's important for us to be able to model the seasonality in a variable. We need to be able to say what part of the variation or the change in a variable comes from just seasonal changes, patterns that repeat every year, and which part of it's coming from everything else, random variation due to demand shocks, or so on. Okay, is this streaming okay? Can someone say yes? Because otherwise, I think last time I was just talking to myself, I think, for a while. Is it all working all right? Hello? If you could let me know if there's any... Alright, let's keep going. I just want to check, so last time, if people could just now and again just let me know if things are alright. Okay, so we need to be able to determine what part of the change is coming from seasonal variation and which part is not. Okay, so this is why often when you have data, if you've seen real data, sometimes say GDP or so on, or they talk about changes to sales, etc. in the news, you see them when they've made some seasonal adjustment. So you'll see that the data will say that the data comes seasonally adjusted. And what that means is that they look at the variable, they determine what they see as seasonal variation, and then they take that variation away. And we'll give examples of this. So seasonal adjustment is essentially modifying our variable so it's that we remove this seasonal variation, these repeated seasonal patterns. Once we do this, we're just left with the random variation, the variation due to demand shocks and so on. We're left with kind of the more economically interesting variation in a variable, not that which is just driven by a seasonal pattern. So we can see then, once we start looking at seasonal adjustment, we need to make some assumptions about what the form of the seasonality is. It's not necessarily obvious, it's not immediately obvious to say which part's seasonal and which part is non-seasonal. So we can make some assumptions, we give examples, and we can then adjust the data. But again, this adjustment could have undesirable side effects. Namely, we may think something's just seasonal variation when it might not be. It might come from some underlying economic factors or so on, which are interesting to us. So again, we may think that some of the variation is seasonal when it's not, or so on. So again, we may adjust the data too much, for example. We may take out too much of the variation. Okay? So let's stop with any questions as we go down. So there's two forms of seasonality: deterministic, which in essence means that the seasonal pattern repeats exactly in a fixed way every year, or stochastic, namely that it doesn't repeat exactly, say, quarter on quarter each year, but that say there could be a shock at quarter 4, and that could kind of permeate. So every quarter, if there's a big sales shock, it could mean that sales are high next year, and then 4 quarters ahead and so on, but this will eventually die away. Okay, so we could think of that the seasonal patterns there every year, or that there's some shock at some year and this effect essentially dies away. There's a seasonal effect but it dies away after so long. Okay, so let's give examples then. So we gave this example then where we saw for sales, the growth rate in sales, we can see that there's this same pattern every year at quarter 4. There's a big, the quarter 4 growth is much bigger than all the other quarters. It's not the same every year, but we can see every single year it's always much higher than the rest. And the same for quarter 1. It's always very negative and much less than all the rest. So it looks like this is a variable where the mean is different in every quarter. In every year going across, the means within the average in each quarter, we can see the average in quarter 4 is very high and positive. The average in quarter 1 is very negative. So we can see that it's highly unlikely that the mean is staying the same over time. So the most obvious way the most obvious part of seasonality will say that, okay, well, the mean, the average level of sales growth in the quarters varies. So to do this, we can just allow the mean to change. And this is what we did here. So again, we model the seasonality. Then everything else is just random. Everything else is all. This is then the rest of the variation in y when we remove this seasonal mean change. And these dummies take values 1, so d1t equals 1, if t is a quarter 1 observation, and it equals not otherwise, and so on. So these are just seasonal dummy variables. So we can see what this does then, it just lets the mean change. So the average value of y, given q equals 1, well, in this case, d1 equals 1, this will equal 1, all the rest will equal not, and again, the shock has mean not. So we can see the average will be alpha naught plus alpha 1. Then we can do the same for q equal 2, 3. Then in 4, then all of these are not, so we just left with alpha naught. So you can see how essentially these dummies with alpha 1, alpha 2, alpha 3, they allow the mean to change in quarter 1, 2, and 3, and therefore alpha naught is going to be the base mean. It's the mean in quarter 4. So for example, alpha 3 is the difference in the mean of y between quarter 4 and quarter 3, and so on. So these have got very clear interpretations then. Okay, so this simple model will allow the mean to change in every quarter. So then the residual from this model will be all the variation in y over and above the mean. So you can think of it like quarter on quarter sales. As I said, I gave the example in lecture. Often when they report Christmas sales, they'll report the quarter on quarter growth rate, which means they compare how much growth rate is this Christmas relative to last Christmas. It's the differential between the two that's interesting. It's because sales are always high in Christmas relative to the rest of the year. It's not interesting to say that the growth rate's 5 or 6%. The question is that higher than what it was last year or the year before, and so on. Okay, so this is why we want to adjust. We want to be left with just the variation over and above the quarterly change in the mean. Okay, so hopefully everyone's clear how epsilon t, once we remove this, if we knew all these coefficients, we can subtract this out and would just be left with then this variation epsilon t, which is all the rest of the variation in y over and above the mean. So now, so we could seasonally adjust by removing from both sides this seasonal term here. So we could seasonally adjust our data. So then, has anyone got any questions on this so far? I think this is relatively straightforward to understand. So we could seasonally adjust. If we know that yt, that's a minus now, will equal epsilon t. This would then be, we could call this yt star, which is y minus this seasonal factor, the mean, and then this will just equal the residual. This could then be our new variable. This is now all the variation in y over and above the mean. So there is no seasonal change in the mean now of this new transformed variable. Okay, so this is one way we could seasonally adjust the data if we thought the only seasonality came from change in the mean. Is it still working okay? Okay, so let's go down. So this is one of the problems which I mentioned. This plots a correlogram of the sales in growth. It plots the correlation patterns from here. So we can see if we don't adjust this data and we just plot the correlations in this data, then we're going to find extremely strong correlations between y and y so many periods back, because we can see there's this very fixed pattern occurring. So we can see, for example, the correlation between y and y 4 periods back is going to be positive. We can see if there's a big spike in sales, there's a big spike 4 periods ahead and 4 periods ahead and 4 periods ahead. So again, we'd expect to find a strong correlation at lag 4, and so on. At lag 1, we'd expect a negative correlation, because we can see there's a big shock. If there's a big shock now, next period it goes down, and so on. So we can see that we'd expect to see extremely strong correlations in this data set, even though really it's likely that it's just the fact that the mean's changing every quarter, and there may be no correlation between y after we take out this changing mean. Okay, so again, we're finding correlations in y which have been driven by the fact that the mean's changing every quarter. So it's not really a correlation, it's not really a dependence. We're finding a correlation when really there may not be any. It could just be that the mean is changing. So of course we want to remove this out, which is what the seasonal adjustment does. The seasonal adjustment will remove this changing mean. Then we can look at, well, what's the correlation pattern in the rest of the variation in y over and above the mean. Okay, any questions so far? So we can see, as we expected, the correlation without any adjustment, strong correlation at lag 1, negative, strong positive correlation at lag 4, and again at lag 8 and 12, because again, for the seasonal pattern, every fourth quarter it was high, always. So we'd expect to find a big correlation, big positive correlation every 4 lags going back. and it doesn't really die away. It stays very large. Okay, so if we looked at this, we would think that there was an extremely strong correlation pattern in gross sales, but actually it's more likely the fact that there's just a changing mean. So to look at what's the correlation pattern, we need to remove this mean change. So this is what seasonal adjustment does. In essence, it adjusts by removing this seasonal mean change. So as I said before, YT minus this mean change will just equal, well, epsilon t, be the residual from this regression. This could be then our seasonally adjusted data. We then work with this variable here. Okay? So we can then look at, well, what's the correlation pattern in epsilon t? Well, again, this is another way of writing it, again, an equivalent way of letting the mean change. Well, we can run this regression, estimate all these coefficients, and then take our fitted residual, and we can do this in eViews. Just run OLS, take the residual, all these will have hats. Then we'll have a hat here. Then we can plot the correlation here. So this plots the correlation in the residuals from a regression of y on these dummy variables. Okay, we can see that there's much less strong correlations in the residual, as we'd expect. We're not finding these extreme correlations. So we can see that there's some, again, there's some oscillating pattern here. It's negative, positive, negative, positive. Okay, and then negative, then it goes down to naught here. So we do see some correlation in the error term. Okay, so that's deterministic seasonality. Now we might think that there's still remaining seasonality here. We may think that these correlations at the first 4 lags, because remember the data is quarterly, we may think that this also reflects some seasonal pattern. But this could be what's known as stochastic seasonality. Namely, if there's a shock at quarter 4, say, even over and above the mean. So remember, this is the change in y over and above its mean. It could be that when there's a shock, say in quarter 4, that this will mean that 4 periods ahead, even above the mean, it will likely that sales will also be higher, but eventually it will die away. Yep. So again, once we've demeaned, there is no now mean change in y, but this would say if there's some shock at quarter 4, that positive shock, that would mean that 4 periods ahead, on average, also would expect to see a increase in y over and above its mean, but that this would eventually die off because the correlation is only 0.3. So is that clear? Is it clear what stochastic seasonality? As I said, it's also a seasonal pattern, but it dies away. So we may think, and the point with stochastic seasonality is, well, do we really know that this is seasonal? Do we really know that this correlation at lag 4 over and above the mean, is it seasonal or is it not? Well, this is the point where we have to then make some assumptions. And there's no real right or wrong way of doing it. It's just often we would assume that because it's quarterly data, any correlation up to lag 4 could come from some stochastic seasonality. Okay, so then so what this is saying is, even after removing the mean, even allowing the mean to change, it may be that there's further seasonality in these error terms here. So we may want to remove more of the variation from y. So for example, maybe that we have a quarterly AR1 say, where YT depends on YT minus 4. Then we would say all the rest of the variation was coming from economic or other random factor. We may think seasonality is driven just by this part here. Maybe that YT depends upon YT minus 4, and that's just driven by seasonality. And then the rest we may say then is variations from economic factors or shocks or so on. Okay, we can see this would be known as this. We can think of this as stochastic seasonality, where it dies away. If theta 4 is less than 1, we know that any shocks 4 periods ahead, the effect on the future will die off. Okay, and again we can see, well, what kind of, you should work through this. We could then work out, well, what correlation patterns would we get from this model here. And remember, we've already done this for the case. Remember in exercise 2, we looked at this model here, and we derived the mean, the variance, and the correlation and the covariance function. This is exactly the same now. We can work out the MA infinity form and see what kind of correlations this will allow. And what we'll find is it will only allow correlations at lag 4, at multiples of 4, and they'll be not everywhere else. Just like here, we had correlations at all lags of multiples 2, and they were not everywhere else. So again, work through this. We come back, substitute again and again, and you will find the MA infinity form written like this, where the coefficients satisfy this here. So again, from this we can derive, from this we can use the formulas for the covariance function of an MA infinity, plugging in these particular coefficients. So if you see this looks exactly like we did for the AR2 model. So again, look at the answers to this when we did this case. It's exactly the same. We could do the same if we had a YT minus 3 and so on. Okay, so what we find is then this model will only allow correlations at lags multiples of 4, 8, 12, so on. All the rest are not. So we might think that these correlations just coming at these quarter 4 are coming from seasonal factors. Okay. We could allow more general models. We might think that the seasonality is driven by YT being correlated with its level for period and the shock from last period. We could have this seasonal ARMA 1-1. Okay, or we could combine, which is more realistic. We may think that the means change and that we have some seasonal pattern governed by this, for example, and so on. We could specify any model here, but what the assumption would be is all this variation in Y is just seasonal. Then everything left is just essentially all, the economic variation, you could say, or variation from just random factors and so on. Yeah. So again, this is the point. The point the first slide was getting at. We may attribute some of the variation to seasonality when it isn't. And the question, and again, the course, we don't go into loads of depth on this. It's just you need to just understand it, just the broadest level. What would we suggest was seasonality and what isn't? How do we know? We can never really know. We just have to just assume what we think is seasonal, and then the rest we're saying is just economic variation. Things like allowing the mean to change is not particularly controversial, but specifying which part of a stochastic variation is. For example, we may want to have why not have this there as well, this shock, and this as well? Why is this not seasonality, and so on. So hopefully you see the point that where do we draw the line as what's seasonal variation and what isn't. Okay, so often it depends on the data set. Often in certain literatures, there's normally common ways of doing these things. Again, it's often a little bit ad hoc. It's not really governed by theory. Often it's difficult to really determine or say or prove what is seasonal and what is not. Okay. So if you thought that if you thought that all this was seasonal variation, then you would run this regression, estimate all these parameters, and again take the residual. Then you would use this as your seasonally adjusted data. So if you believe seasonality took this form, you'd run this regression and you would estimate this. You would then take epsilon t as your variable. You would let's say this was retail sales, and this may be given to you on wherever you find data online. It may be given in a seasonally adjusted form. Okay. So again, this was a correlation pattern after we removed. Going back to the retail sales, this was a correlation pattern when we removed when we remove the means, we may want to allow a more general model. We may want to, this regression here runs this regression for the sales data. It now includes these two variables here. Well, these are the seasonal dummies. Seasonal dummy 1, 2, 3. This is the coefficient on yt minus 1 and yt minus 4. So we see they're both significant at the 1% with very small p-values. So we find there's strong probability that both the coefficients are non-zero. And we see a positive coefficient on lag 4 and a negative coefficient on lag 1. As we'd expect, because there's a big negative drop in correlation in sales at lag 1 and a big positive correlation at lag 4. So we can see then, well, we could see, we may think that we've modeled all the seasonality here, such that the residuals from this regression no longer have any seasonal variation. And the way to look at that would be, well, we can test whether the residuals from this have any serial correlation. And this does the test at up to lag 4. This just means up to lag 4. And we see testing with this test that the errors are an AR4 have an AR4, whether the errors are AR4, and we find evidence that they're not. Remember, the Bruce-Godfrey test has the null hypothesis that there is no serial correlation against the alternative that if there was correlation, it would have an AR4 form here. It does it to lag 4 here. So we can see that once we've controlled for all these factors, the residuals no longer have, there's no longer any correlation at lag 4. So this might be enough then to say, well, there's no now correlation over the last 4 quarters. So we've removed all correlations and variation coming within the last quarter. They may then use this demean data to then perform the analysis. If they wanted to look at the effect of retail sales growth on house sales growth or industrial growth, they may for each variable run this regression, strip all that variation out and take the residuals and then do their regressions on the residuals. Namely, what this test did was basically run this. What this last slide did was run this regression here, included all these variables, found that they're all significant. Then it tested for whether there was any correlation in this here up to lag 4, and we found that there wasn't any correlation. So that may be enough then for a researcher to say that we've removed all the seasonal variation. They would then run this regression, take the estimated residual, and they'd use that as their variable then. So they may regress, say, epsilon t of, say, retail sales on epsilon t of, say, industrial sales. This would be the variation in industrial sales over and above the seasonality, and this would be the variation in retail sales over and above seasonality. They then look to see if there was any effect, any relationship between these two variables. Now, having both removed all this seasonality. Okay, so that's everything on seasonality. Are there any questions on that about what I've said, or? Hopefully people are still there. I've not just been talking to myself for the past half an hour, have I? Has anyone got any questions? So I finished. That's everything I wanted to say on seasonality, unless there's any other questions. Does anybody have any other questions about the course or any of the lectures so far? Any other questions? I'm still not sure if he's working on it. Okay, well, no one's responding, but nobody emailed any questions. So you've got, is that no? Okay, so no. No, is that okay? Well, is that a no to it working okay, or no to no questions? Anyway, if you've got a question asked, we could go through it. I may put on another live stream towards the end of term. I think when people start revising, maybe these sessions will be more useful. Maybe. Do you think they'll be? Would these sessions be useful a few weeks before the end of term? Okay. Well, this was just a trial. I hope the stream was useful. I'm not sure how useful it's been, but I'm still getting to grips with it. But we could have another one, or could have some more at the end of term if people have questions. So if you have questions later in term, then email, and we can do them in office hour, and also we could do it on here as well, and then we can save them for other people to watch. Okay, so I think if no one's going to ask anything then, I think I'll leave it then. I'll edit this clip, and it will go on my channel if anybody wants to watch any of it again. So as I said, just email any questions, and we can have another stream later in term. Okay, so leave it at that. Thank you.